Okay, so today Greg and I are going to be talking about some of the things that you can do to improve the energy efficiency of air-cooled and water-cooled chillers. Fundamentally, how a chiller works is you have a high pressure side and a low pressure side. The high pressure side is the hot side. That is the side of the condenser. On the low pressure side, the low pressure side is the cold side. That is where you have the evaporator, and the compressor's job is to take low pressure refrigerant on the evaporator side, compress it, and send it over to the high pressure side. Just about all of the energy used by a chiller is consumed by the compressor. And compressors use a lot of power. In fact, it's not uncommon if you walk into a building or a campus for the compressor motor to use as much as 25 to 35% of all of the energy used by the area that the chiller serves. So if it's serving a 300,000 square foot building, you could have 25 to 30% of the building's total power being used by one motor and that's the motor running the compressor. And so the amount of work done by the compressor depends on two things. One of them is by the difference in pressure between the low side and high side of the system. What's the pressure difference between your evaporator and your condenser? And the second thing is the amount of refrigerant that it has to compress. How much refrigeration is circulating through the system? So knowing that, there are two ways to decrease the amount of compressor work.
Getting into it, I'm going to jump into kind of some real world examples of things that we've done and had success with on reducing overall chiller plants energy, and kind of giving you some examples of what works, when you can get away with doing, for example, warmer chilled water. I'll kind of break down some different strategies you can adopt for programming, or just identify how to go about that. So we'll start off there. We'll start off on the chilled water side of things. I think this is probably the most well-known, if you will, of opportunities out there. So what I've got depicted here is this enthalpy diagram representing basically bringing the floor up, I like to think of it as. So by creating warmer chilled water, we bring this pressure of the lower operating pressure of the compressor where it's starting to work, to take the work, bringing that up. So it's starting from a warmer pressure or warmer temperature, higher pressure. Overall, that reduces the compressor work. So it's represented here by the smaller arrow, basically. So I'm penciling out, you go from 44 to 50 in this case, and then I'll kind of break down, how do you know when you need 44? How do you know when you need 50? What we've found really good success with in doing that is to combine a reset in place that automates the pressure and the temperature to kind of work in tandem together. So this is, I've got represented a hospital here in Phoenix that we implemented both of these resets in place. And this is in August. So you can see the bottom graph here, the blue lines, we're consistently getting above 100 degrees every day. The red line is chiller plant efficiency. So this is total chiller plant energy and efficiency kW per ton, not just chillers. So it's accounting for towers, fans, and other pumps and everything. The middle line here is the system pressure and differential set point. And the top graph is the current chilled water temperature. So what I want to bring your attention to is initially we were always running at a fixed 22 PSI. We implement the new programming here, and you can see that pretty much every night, even though we're in the middle of August hitting 100 degrees days, we're able to back off of that 22 PSI, or basically that design pressure set point. So dive a little bit deeper into this is talking about, well, how do I know, or what valves do I want to look at? And the answer is not necessarily the most critical, and not necessarily the end of the line, but something that represents the general profile or needs of your building. So, you want to grab an air handler that opens and closes throughout the day or throughout the load profile, if you will. You don't want to pick an air handler that's always pegged or that's always satisfied. That's why you would kind of throw out first in the line. And end of the line is maybe arguable, but that's that one's usually going to be the first to start, right? So you don't necessarily want that driving the train all the time.
The most common way of saving energy on air-cooled chillers. And in fact, for most people, the only way that they know of saving air on an air-cooled chiller is to raise the chilled water temperature. And doing that is a good idea. You can improve the system efficiency by about 1.4 or 1.5% per degree of increase. So for example, if you were to, just to make the math easy, if you were to take a chilled water system that was running at 40 degrees and raise it to 50 degrees, you'd have about a 15% reduction in compressor energy. With water-cooled systems, it's even more than this, but with air-cooled, it's typically about 1.5% per degree. So any little bit that you can inch it up will make a measurable difference. Now, the less obvious part of this, we're familiar with raising the chilled water temperature, but you can also, it's also important to raise the evaporator temperature. And you might wonder what's the difference between the two. One thing that we wanted to mention is that it's worth reaching out to the utility company to find out if there are incentives or rebates available for any of the things that we're talking about today. Greg was talking mostly about recommissioning or retro commissioning opportunities, ways of adjusting your system, getting it to run the way it's supposed to run again. And the ones I'll be talking about for the air-cooled chiller have more to do, or generally fall under the category of capital upgrades or improvements. Contact your utility provider early. We see more projects miss out on rebate and incentive opportunities because they don't include the utility early enough than for almost any other single thing.